With the corrected scores, the coefficient for the long string was 21.2. The coefficient for the short string was 22. So 21.2 and 22.
Yeah.
Statistically, they are quite close.
So it has to deal with the length of the wave, no, it's the wavelength
Yeah, it's the
because,
wavelength that we change.
yeah.
Yeah.
So it's the amount of wavelengths, but that doesn't change, like the actual relationship between the wavelengths and.
It's not even the amount of wavelengths, it's just the length of.
It's like the length that you're measuring, because when we measured half, or I guess like a quarter or whatever, like the smaller amount, we had like the coefficient was like 10.
Yeah,
And then we had the,
mine is 11,
yeah.
and I still have the half wavelength for the short string, so 22 makes sense.
Yep. Now, and this is where I'm going to try and take just sort of a teacher direct help here for a little bit. We are making it into the equation. After we sort of figure out our y is equal to 1 over x, we plugged in y is equal to 22 times 1 over x. After we have that, we usually plugged in the variables. Right? We plugged in the letters. Right? So, what are the letters that we've got here? What's on our y-axis and what's on our x-axis?
Our x-axis is frequency,
Mm-hmm.
it's hertz.
Y is wavelength.
Okay.
So that would mean wavelength equals 22 times 1 over frequency.
Wait, can you explain that just one more time?
Yeah, so, we were plugging in the variables, so on the graph, the x-axis is frequency, so you would replace x with frequency,
Oh, okay.
and y with wavelength.
Sorry, I just
Mhm.
put it up.
Yes. Are we sure about 22? That's right. For the coefficient?
Yeah.
On the
Yes,
short
on the
string.
short string.
Or on the short string?
Yeah, that's the,
Wait, I feel like this is very obvious, but why are we multiplying 22 by 1 over x? That equals y. That's a long
Because that's what it is on the graph.
yeah, that's the trend line. You could like label the,
Oh,
thing is, that like that's equivalent to, I don't know how to say it, like the portion of the wavelength you're measuring, I guess. I never can think of a better phrasing, but
That's
it's,
just one full.
yeah, that's a full wavelength, but you can change that. Where like if, like in mine, I still have the half wavelength for all my data, so I'm just gonna have that as 11 instead of 22.
Well, then you'd have to put that it would be half a wavelength as y instead of a full wavelength.
Yeah. But it's, maybe, I guess 22 would stay for this equation, but it changes.
Yeah, since it's equating the for a full wavelength.
Yeah,
So if it's for a full wavelength, we think it's gonna always be 22.
yeah.
If it's for a full wavelength, it'll always be 22. Yeah, depending on how many wavelengths or like what portion of the wavelength you're measuring are coefficient.
Can I-
Say again?
Can
So,
I add, sorry, you're good. I'll let you finish it up.
so we're just saying that like for one full wavelength, because on both graphs when the full wave, we were measuring the full wavelength, our coefficient was about 22. So we're saying for one full wavelength, our coefficient's gonna be 22. But then depending on how many wavelengths you're measuring, that coefficient would change, because when we measured half of a wavelength, it was like 11.
I think, yeah.
Yeah.
I love that you guys are focusing on the coefficient, because that's where I had hoped that you would go. I'm going to try and give you a little bit of a breadcrumb as we've started to talk about in this course. Can you guys try and think about units for a second and what these things are measured in order to try and figure out conceptually what the coefficient actually represents, okay? Anna actually mentioned it. I'm not sure if you guys picked it up. I did because I was waiting for that breadcrumb, right? Anna mentioned a while ago of like, what's the coefficient all about, right? Then Zach said, are we sure about the 22, right? And then we're saying, is this the number of, right? And then Liza opened up Desmos to try and look at like, what happens if we were to change the coefficient, right? Here's a challenge for you. What are the units that are actually being measured here? Let's focus on units. What is wavelength measured in? No, frequency. Yeah, what is hertz really?
Oscillations per second.
Yeah. You guys want to open up your background readings? Look into frequency. Oh, I don't know, highlighter. Frequency. And hertz. But hertz isn't a standard unit. I remember we're always talking about we're using standard units. What is a hertz?
The one that we do tonight.
Right, yeah, I think it would be number 1 in 15.1.
There was one.
Was there a formula that we had for frequency?
Yeah, it's just, because they said in the textbook it's the same as other oscillators.
Right, but frequency, what did we relate frequency to? What did we measure last time? We didn't measure in frequency for our spring mass oscillation lab. What did we measure in? And period. Did we measure in period? What's period measured in?
Time.
Seconds. Frequency is measured in hertz, but there's a relationship that combines frequency and period.
Would it be like oscillations per period?
This should have come up in your reading, and this is one of the this is where this leap is going to be.
Oh, the hertz is the number of times.
Wait, the period is the hertz is the
In a
how many,
certain place, is that too bad?
because how many of it repeats per second?
Right, yeah.
Instead of oscillations, it's the pulses per second.
Right.
Okay, on the end of page 421 for the reading, it says the same number of crests per second must enter the boundary of lead. If the speed v gets slower and the frequency f stays the same, then according to the equation, v equals f wavelength. The wavelength must decrease.
What was the page again?
421.
Not sure.
It's like a little pin that
Oh, okay.
Unfortunately we're running a bit short on time. You should have been in our readings a number of times that frequency is the same thing as 1 over period. It's just the opposite. It's the inverse. Period is the number of seconds it takes for one cycle, and frequency is the number of cycles per second. Right? They're inverse of one another. If period is seconds, then frequency is measured in 1 over seconds. That's what hertz is. Does that make sense to everybody?
Yeah.
So,
So I guess I'm trying to come back to this, that if you have wavelength is measured, I'll try and go orange here, in meters. Oh, keep that. Frequency is 1 over seconds.
Is that
1 over 1 seconds.
Yeah, that's kind of weird, isn't it? 1 over seconds? Isn't that kind of weird? This is that math sort of leap.
It would be 1 over seconds to the negative first. But on the top, it would be,
Just try and think algebra. If you have wavelength over here, a number, and then 1 over frequency, algebra, what can we do if something is in the denominator down there?
what's the
Okay.
difference?
You multiply
Multiply, and what happens to it?
that?
It flips, but where does it end up?
On top.
It's just, and then frequency over 1.
Yeah, right? Can't you just multiply the whole thing by frequency?
Yeah.
Right? If that happens, how does the equation change? Frequency times wavelength, right?
Yeah.
Equals 22.
Frequency times wavelength at the moment is sort of equal to 22, right?
Yeah.
But what is wavelength measured in?
Meters.
What is frequency measured in?
Or
Hertz or
1 over
1 over seconds.
if you're multiplying 1 over seconds times meters.
Meters is M over 1.
Oh,
meters
that.
over seconds.
So it's meters over seconds is equal to 22.
Meters over seconds is equal to 22. This comes back to Anda's original question. Meters over seconds is the unit for what?
coefficient?
Meters per second.
That,
Keep going.
It's the,
is the
the
coefficient
last,
how fast?
the last Harkness we came up with the square root of meters over seconds, right?
Well then, Anda, keep going.
That's all I have.
Well, that's how fast the wave is traveling.
Yeah,
So the wave is traveling at 22 meters per second, is what that 22 says. Okay.
But it's not
Can we-
speed? Is it
before we-
law?
sorry, but, before we go past it, can we just briefly restate how we got to the meter per second? I was kind of confused.
Yeah, I'm trying.
Um,
I'm gonna try and zoom out so we can have a look at it. And this is that math challenge, right?
Yeah.
So if you have like anything, if you put it over 1, it's equal to the same
Yeah,
thing.
yeah, I got that.
So it would be, if you have 1 over x and m over 1.
Okay, yeah, I just, I think it was just because we moved from this equation, which has all the labels, to the
Yeah.
other part, and I lost where it was like, you know, the frequency is the 1 over second. And then I lost that wavelength in meters.
That made me more confused.
Yeah, so 1 over x sort of.
Okay, so let me try and see if I can't try and
I just
combine.
need like a summary of what just happened.
Right. So, does anybody want to take over, or would you like me to? Just because I know we're running short on time, and I feel bad that, like, you know, in a true Harkness, But again, this is one of those days where I think we're talking breadcrumbs, right? We're doing our best to. I'm trying to give you only the breadcrumbs that you need, right? If we have an inverse equation, then we've got the fact that this goes down, you have an exponent of about -1 and the number 22 in front of it, frequency and wavelength. Well, then x to the -1 does mean that it's just in the denominator. We said y is equal to 22 times 1 over x is kind of our equation there, right? Well, on the y was wavelength, on the x was frequency, and we could just take frequency out of the denominator and kind of bring it over to the other side, right? In my algebra brain, I'm like, oh, it's in the denominator, just pull it over there. You know what I mean, like, right? So then frequency times wavelength is equal to 22. Now, frequency is measured in 1/2. Wavelength is measured in meters. When you're multiplying the two, it just becomes meters per second, which is the unit of speed. Now, the crazy thing about this, and the bell's going to ring in a second. Please, let's try and wrap up. And we're finishing a bit early, so a bit late, so we're missing time on the
That's okay.
reflection. But watch this, you guys. If that's the case, watch what ends up happening. We're talking about frequency, and we're talking about wavelength. Well, then, if we say that frequency times wavelength is equal to 22, sounds kind of odd, but let's try it. Frequency times wavelength.
Wow.
As you change the frequency, does the speed of the wave change?
No.
No. Frequency times wavelength. All the same values, okay? Now, where I wanted to go, and I'll just leave you with this, okay? This idea of the fact that we just figured out the speed of the wave by looking at frequency and wavelength, the wave formula, again, if we had another 10 minutes, and maybe we spent a bit too much time on the prep, right, is that velocity is equal to frequency times wavelength. And I think we were about 10 minutes away from getting there, right? And I apologize that my timing was a little bit off.
That's what was in that's what I read, it just didn't make any sense.
Right, okay. Now, here's what I would say too. That formula has been applied to architecture and how you actually build for earthquakes. The wavelength of the earthquakes we know. If you build at the wrong size for the same wavelength of an earthquake, your building collapses. It's been related to atomic physics. In that, do you remember who was the first one to figure out that the nucleus was in the middle and there are electrons going around? What was the model? Remember the Bohr model? Bohr figured it out from that formula. He figured out where the electron goes around from that formula. Musical instruments are designed looking at frequency and pitch and wavelength of how big the instrument is. That's why a piccolo is different from a flute. Frequency times wavelength.